So let's see here. So today we're talking about antiderivatives. And so today's a little bit weird. I have a math meeting I got to go to in the middle of class. And I miss these sometimes for the sake of teaching. And then I have this sense of like, what did I miss? So like, I thought, how can I make the most of today and not like cheat you guys out of class? Well, so what I have is a worksheet on anti-differentiation. So like I'll leave in about 15, 20 minutes. And then one of the GAs or I don't know what he is technically, but anyway, Audric is going to come and sort of help you guys work through the sheet. I use the plurality. I hope that that's honest. I don't know. We'll see. I know people have things across campus that keep them from being here when class starts, but that's cool. So let's just talk about what is anti-differentiation. What is it? So it's kind of what it sounds like. I mean, here's the definition. We say big F is an antiderivative of little f if big F prime is equal to little f. So an antiderivative of a given function is a function whose derivative is the function. So, example. We could have little f of x equal to, let's say, x squared. All right. Then to calculate the antiderivative, sorry I had to start on time. I have to leave early is why. No, I'm just saying, like, particularly today I would usually have waited, but I have to leave like about 15 minutes from now, and then I'll come back. I have a worksheet for you guys to do. Right. So if the function is x squared, then the question is, how do you anti-differentiate that, right? So your goal is to put big F of x, fill in this blank, then, right, df dx equals to x squared. So how do you fill in that blank? What function, when you differentiate it, gives you back x squared? Remember, differentiation lowers power by 1, right? So it's got to be a cube. So we could try x cubed, right? Would that work? Not quite, right? Because if you differentiate x cubed, you get 3x squared. So how do we fix that? Divide by 3. All right? So 1/3 x cubed, or let me rewrite that in a more civilized fashion. I mean, anyway, I kind of like to write that as x cubed over 3 for the sake of the board readability. That's the antiderivative of x squared. All right? I say it's an antiderivative because f of x equals x squared also has, let's say f of x, well, let me call it g, just big G of x, equal to x cubed over 3 plus any constant, right? Put any constant there that you want. What happens when you differentiate it? G prime of x is still equal to x squared, right? So you can take my antiderivative of x cubed over 3. You can add any constant to it that you want. 1, 2, 3, 4, a million, doesn't matter. All right? So what does this mean? This means that our choice of antiderivative is not unique, right? right? So if you had two different antiderivatives, right? Say f1 and f2 are both antiderivatives for the same function f, right? Let's think about that. If f1 and f2 are antiderivatives of f, then what? What does that mean? That means that f1 prime of x is equal to f of x, but it's also equal to f2 prime of x, right? Now, what did we learn? What did we learn like a week or two ago? If the derivatives of two functions are equal, how are the functions related? Supposing it's true on a connected interval of real numbers. We learned that they're related by adding a constant, right? So this implies that f1 of x is equal to f2 of x plus some constant, right? So for a given connected interval, the ambiguity, all right, the ambiguity in the antiderivative, there is an ambiguity, but it's just the one I've already shown you in our examples. It's the fact that you can add a constant, any constant you like, and you still get an antiderivative, right? So for this reason, we make a definition. The integral of f of x dx is the most general antiderivative of f. So what does that mean? That means that it's our custom when we talk about, and this, by the way, this symbol is called the indefinite integral. Indefinite integral of f of x, all right? It's the most general antiderivative of f. And all that essentially means, because of what I wrote right above in red, is we always have to add a constant to the most general antiderivative. So let me show you some examples. So first of all, let me go back to my integral of x squared dx. Well, this is equal to 1/3 x cubed plus a constant. So the key with the indefinite integral, it's kind of silly, but we have to add a constant. That just recognizes the fact that there are many choices for that constant, which will still be, a function that when you differentiate, right, you go back to the integrand. This f of x is called the integrand. So here x squared is the quote-unquote integrand. So we'll spend the lion's share of our time on finding indefinite integrals. All right, but sometimes we like to talk about antiderivatives. They're really just two different words for the same idea, more or less. I would say this, if I wanted to be picky, the antiderivative or an antiderivative is a specific function. Technically speaking, in my view, the indefinite integral is actually a whole set of functions. It's a whole set of functions where the set of functions just differ by a constant, all right? But anyway, long story short, if I ask you an indefinite integral and you don't add a constant, I take off a point. And after about the 40th time I do that, you're like, I will add a constant already. Stop taking the point off, Or probably you'll just add a constant. So anyway, it is our custom plus c. You don't have to put c. You could put plus b there. You put whatever notation you want for a constant. I just typically use c, all right? All right, now that we got that in front of us, let me give, yeah? Oh, okay. Let me give you more examples.
I can take a picture of it.
Oh, absolutely. Yeah?
Sorry.
Oh, you're fine. That's cool.
Did you erase anything?
Just that. Uh-huh. Okay, so, all right. Let me draw a picture of the mechanics of what we're doing, all right? So here's what's going on. We are integrating f of x dx, and we're saying it's equal to big F of x plus some constant, all right? If this is correct, right, if we're correct, then it has to be the case that we can take this, right, and go back to here by taking the derivative. So these are like inverse processes. If you differentiate the antiderivative, you should get back the function you started with, all right? And so every one of these every antiderivative we guess, you're like, yes, all of integration at its base is educated guessing. It's all educated guessing. So I'll call this example 4. I don't know. How about this? Integral of e to the x dx equals to what? You guys tell me. What function, when I differentiate, do I get back e to the x? How about, I'll do it for you, e to the x, right? Now, how do we check that it worked? The check is just this, d dx, right, of e to the x plus a constant is e to the x, right? Which is what we wanted to get. If we're successful in our integration, this thing we're doing is called integration, then when you differentiate your answer, you should get back to the integrand. We can always check our work. Now, this next one's a little bit trickier. But here's a property. Here's a property of the indefinite integral. You can break it up into pieces. Like it's the integral of x dx plus the integral of e to the minus x dx. Like that's how this works. All right? So you can break it into two problems. First of all, the question is, what's the integral of x? What can I differentiate? We saw the integral of x squared was x cubed over 3. So if the same pattern holds, we should try add 1 to the power, right? So x goes to x squared. But does that work? If we just put x squared here, is that going to work? Well, no, not quite, right? Because when you differentiate x squared, you get a 2, right? So we have to divide by 2. So 1/2 x squared. And how about this? What if I just put plus e to the, what if I just put plus e to the minus x? Is that going to work? We should check our answer, right? I'll check my answer in red. So let's try it out. d dx of 1/2 x squared plus e to the minus x. And you can drop the constant. The constant always differentiates to 0. It's irrelevant. Right? When we're checking our work, we don't have to worry about the constant. So the derivative of x squared is what? So we got 1/2 of 2x. Well, that's good. Gives us back the x. But then the chain rule tells me minus e to the minus x. Uh-oh. It didn't work. Right? We did not get back. This right here doesn't match this right here. See that? We've got a minus on the answer, but we got a plus if we go back by differentiation. Remember, antidifferentiation is an inverse process to differentiation. If you differentiate the antiderivative or the indefinite integral, you must get back to the integrand. We didn't, therefore, this is incorrect. How can we fix it? It's very simple to fix. Instead of putting a plus here, put a minus. See that? If we put a minus here, that puts a minus here. I'll do it in purple, right? And then that minus cancels against the minus 1 from the chain rule, right? When we differentiate e to the minus x, we get minus e to the minus x, right? So minus minus gives you plus, and we've got x plus e to the minus x, which is what we had over here to start with, right? So in the worksheet I have you guys doing today, every time you write down what you think is your antiderivative, I insist you check your answer. You must differentiate it and show that you get back to the integrand. I've tried to leave you space in the worksheet so you can write the derivative below your, I left you a blank to write in the answer antiderivative, right? And then there's space underneath for the most part to check your answer. How do you check your answer? You differentiate, right? Let's see here, example 6, integral of cosine of theta d theta, let's say. Use a different letter. Well, what function, when we differentiate, did we get cosine? Sine, right. And so, is this true? Well, yeah, this is true because d theta of sine theta equals to cosine theta, right? And that's what we got over here. So we differentiate the antiderivative, we get back to the integrand, we're good. All right, let me bump it up a notch here. Example 7. What if we had the integral of sine of 3x dx? Well, let's see here. Derivative of cosine is minus sine, right? So it seems like I should maybe try minus the cosine of 3x plus a constant. Does that work? Let's try it out. What happens when you differentiate my alleged answer? We get sine of 3x, and I'll write down the chain rule, ddx of what? 3x, which is, 3 sine of 3x. Oh, no. Well, this is no good. We've got an extra 3. What should we do? How can we fix this? Remember, this is an educated guess, right? Minus cosine 3x plus a constant is an educated guess. We checked it, and it turned out not to be wrong. We don't give up. We simply modify our guess to get rid of the 3, divide by 3, right? So if I just divide this by 3, then we got it. All right, so, yeah. Here's another similar example. If I was integrating like e to the 3x dx, what I would do is I would do 1/3 e to the 3x plus a constant. See, dividing by that 3 takes care of the 3 that comes down from the chain rule when I differentiate. You know, the 3 from the chain rule. Did you guys understand what I'm saying? When I differentiate e to the 3x, I pull a 3 out from the chain rule. But then if I put a 1/3 in my antiderivative, that 3 and the 1/3 cancel and just give me e to the 3x, which is what I want in this case. Example 9, integral of hyperbolic cosine of x dx is, well, what differentiates to hyperbolic cosine? How about, it's just sinh, right? Just hyperbolic sine. Remember, we know that the derivative of hyperbolic sine is hyperbolic cosine. All right. You'll forgive me for not checking my work on these last couple. I'm almost out of time here. Example 10, what's the integral of secant squared theta d theta? Tangent, right? Because the derivative of tangent is secant squared, so that makes that tangent. What's the integral of tangent theta? The answer here, what's that? It is not. The answer here is inappropriate. Inappropriate. And in the sense of inappropriate for this lecture, because that requires what's called an integration technique. This we'll learn how to do towards the end of the semester using something called U substitution. So this is for later. Later. But that does go to serve to illustrate a point which I have not made yet, which is there are many functions that you cannot integrate in the sense that we're doing right now, just writing on the formula. Think about the logic of what we're doing. We're asking this inverse question. We're asking, what function, when I differentiate, gives me back the integrand? It's not hard to come up with examples where you cannot just guess the function. All right? But this one we can. How about integral of, let's say, d, I'll use a y for something different, 1 plus y squared. Which function differentiates to 1 over 1 plus something squared? You remember? I asked you to prove it on the test. This, my friends, is the inverse tangent of y. And I was supposed to add a constant up here, right? Take a point off my lecture. All right. So to summarize, I guess I should point out here, there's some general formulas we can, so I've shown you integral of sine, cosine, cosh, secant squared, the inverse tangent. Another one we could do would be integral of like dx over the square root of 1 minus x squared. What's that? Well, that's inverse sine of x plus a constant, because we know the derivative of inverse sine is 1 over the square root of 1 minus x squared, yeah? But let me just, fun fact here, the integral of x to the n dx, what's the pattern? It is 1 over n plus 1, x to the n plus 1, right? Plus a constant. This is the power rule for integrals. So you should keep that in mind as you're working on the worksheet. That's the pattern we've used a couple times today. When does that formula not make sense? This is for what? For n not equal to minus 1, right? Minus 1 is a problem. There is a great asymmetry in integration and differentiation. When does the power rule not make sense for differentiation? When the derivative of x to the n is n times x to the n minus 1, there's no condition on n. It's just true. But here, there's a condition. See, because the integral of x to the minus 1 dx is the integral of 1 over x dx, right? What function, when differentiated, gives you 1 over x? Well, we saw, what was it? Got it? Sorry, I don't have more time. It's the natural log of the absolute value of x plus a constant. Now, I'm adding the absolute value there. I'll talk more about that when we have more time. But the absolute value it needs to be there for the sake of it being the most general indefinite integral. All right, with that said, I got to run, you guys. I'll be back, though, as soon as the math meeting's done, which could be 15 minutes or could be 30 minutes. I don't know. Your guess is as good as mine. But in the meantime, I think the best way for you guys to really internalize this is to actually work a bunch of problems, right? So I have made you a handout, which I will collect once you're done with it. We won't finish it today. Like, get as far as you can, you know. Some of the problems on like page 3 I haven't talked about how to do yet. But,
You can help each other, right?
oh yeah, help each other. Yeah, this is not like a quiz. This is a worksheet. And there should be a, you know Audric. Audric's coming to help you guys if you, while in my absence. So, all right. Again, I shall be back, hopefully sooner rather than later.
Where's the other student? I saw him